Okay, so in this final lesson about concentration, we are going to look at some ways that we see concentration in like our consumer products, right? So if you go and you pick up a product at at the store that is has a certain concentration, you won't see it in moles per liter, right? That's just for um, the chemistry lab. So when we have consumer products, they are written a different way. They're written usually as a percent concentration. So, for example, you might have encountered this if you go to the pharmacy and you pick up hydrogen peroxide at the pharmacy, you'll see that it's 3% hydrogen peroxide, and that 3% is a percent concentration. Or if you enjoy fancy skincare products, you'll often go and you'll see that something is, I don't know, 1% vitamin C serum or something like that. So um, this is how you would calculate percent concentrations. There are a few different types of percent concentrations, um, but they're all calculated very similarly and very similar to the scientific concentrations. So, except they don't use moles. So, the first type is called the mass volume percent. The first thing that you see here is always the solute, and the second thing that you always see is the solvent. So it's always like solute divided by solvent, or they'll say the volume of the solution. And the reason why they say the volume of the solution is that sometimes you don't always add, like the solute takes up space. So sometimes you don't have like a full liter of water that you've added, but you've added water up until the volume becomes a liter. If that makes any sense. Maybe it doesn't make any sense. Um, the the volume, the bottom thing, the thing we divide by is considered like the volume of the entire solution once we're done with it. Then there's mass to mass percent. Okay, and that's the mass of the solute divided by the mass of the solution. So you see the solute is always on top, solution is always on the bottom, right? The only difference between mass volume and mass is in the second one, uh, you need to weigh your final solution once it's done. And then there's volume percent, right? Again, solute is always on top, solution is always on the bottom, right? And because these things are percentage, after you divide, right, you're going to multiply by 100. So it becomes a number between 0 and 100. Okay, so we're going to learn how to work with these formulas, and they're very simple. So it says intravenous fluid, IV fluid, is 0.9% mass per volume of sodium chloride. So this would be like, have you ever heard of a saline solution? Right? Um, we usually use saline solutions to get people's blood volume up. So, and we deliver them via IV. So this is an IV bag, right? Okay. So an intravenous solution fluid is 0.9% mass per volume. And that means that 0.9 grams of NaCl is dissolved in 100 milliliters of solution, right? So the MV percent, mass per volume percent, is the solute over the solvent, or sorry, the solution, times 100. And that will give us 0.9%. Pretty easy, right? So let's take a look over here at a different but very similar problem. So what if we have 12.5 grams of sodium hydroxide in a 250 milliliter solution. How would we find the mass per volume percent so we could write it on the container? We would take the solute and we would divide by the solution and multiply by 100 and get the 12.5 divided by 250 times 100 gives me 5%. Now we have to consider significant figures here. 12.5 has three significant figures. 250 only has two. So I would call this a 5.0% solution. Okay, that was super easy, right? Mass to mass percent. It says mass to mass percent, we take the mass of the solute in grams, divided by the mass of solution in grams, and times 100%, right? So for example, 0.129 grams of magnesium dissolved in 100 grams of seawater would be 0.129% mass to mass, right? So we go mass to mass percent is equal to 0.129 grams divided by 100 grams. By the way, did you know the mass of water is 1 gram per milliliter? So 100 grams is also 100 milliliters. Maybe you didn't care to know that fact, but it's true, right? So we end up with 0.129%. Okay, so let's try a different one. It says determine the mass of NaOH. So we want to know the mass this time. If the mass per mass percent is 3.55 and it is formed with 45.7 grams of NaOH. Okay, a little bit different. So what do we know here? They want us to find the mass of NaOH, which is the mass of the solute. They're giving us the mass to mass percent, and they're giving us the, they want the mass of the solution. I didn't read that correctly. They want the mass of the solution, and they're giving us the mass of the solute part. Okay, so a little bit different. So the mass to mass percent we know is 3.55% is equal to the mass of the solute is 45.7 grams, and the mass of the solution we need to find out. Right, so this is our formula. Okay, so we need to rearrange this to find the mass of the solution. The mass of the solution right now is in the denominator. Okay, we can't solve for it in the denominator. We have to solve for it in the numerator. So what's going to happen here is it's going to go to the other side of the equation, where it will become multiplication instead of division, and the 3.55 is going to switch places with it. Okay, so we have the mass of the solution is equal to 45.7 grams divided by 3.55% times 100%. Okay, the percents will cancel. And so we'll be left with something in grams, which we should because we're solving for mass. So in my calculator, I'm going to go 45.7. And then I'm going to divide by 3.55. And then I'm going to times by 100. So I will get sorry about that. I will get a mass that is 1,287.32 grams. This has too many sig figs. I only need 3 sig figs. But what do we do? Because I can't just write 128. 128 doesn't mean the same thing as 100 or as 1,287. So how do I do this? I put it in scientific notation. So this decimal is going to move 1, 2, 3 places, and I'm going to end up with 1.29, right? 1.29 because after the 8 is a 7, so I have to round up. And I moved my decimal 3 places, so times 10 to the 3, right? Or I could say 1.29 kilograms. Now, the next type of percent volume is the volume to volume. So again, solute goes on top, solvent goes on the bottom. The example says rubbing alcohol is 70% volume per volume, right? That's the stuff we all know during COVID. Everybody had antibacterial solution or rubbing alcohol. They said you could use instead, but it had to be, I think, 70%. So you could make your own solution up, right? So 70, the mass, no, the volume per volume percent is equal to so you have 70 milliliters of alcohol in 100 milliliters of solution, right? So the volume of the solute goes on top, the volume of the solution goes on the bottom, and then times 100%, right? And you would get 70% volume per volume. So when you come up with a percentage, you should write out what the percentage is, right? So in this previous, we should write 0.129% mass per mass. And in the first one, we should write 5.0% mass per volume, because there's 3 types of percentages, right? And so we need to distinguish them from each other. Okay. An example says, determine the volume of hydrogen peroxide that is needed to make 125 milliliters of a 3% volume per volume solution. So we need to know the volume of solute. We have the volume per volume percent is 3.0%. And then it's the volume of the solute, which we don't know, over the volume of the solution, which we do know. Here. Times 100%. So the volume per volume percent is 3.0. and that is equal to the volume of the solute, which we don't know, over the volume of the solution, which we do know. We need 125 mils. Times 100. Okay, so what we're solving for is on the top of the fraction, which is good. It's in the numerator. That's where it needs to be. But we need to move this. This guy is multiplication. And we need to move this. This guy is division. So if we move them to the other side of the equation, okay, they end up doing the opposite operation. So 100 is times. So when we move it to the other side, whoops, I wrote milliliters, but that's not right. This percent. So when we move it to the other side of the equation, it goes on the bottom. Okay. And then 125 mils was divided by. So when we move it to the other side of the equation, it goes on top. Right? So into my calculator, I put 3 times 125 divided by 100. And then I'll get my V solute. So I would need 3.75 milliliters. And then let's check for significant figures. So I need that to 2 significant figures because this percent only has 2 significant figures. So I would write 3.8 milliliters is what I need of my solute. So to make this to make the solution, right, what I would do is I would go and find my 100% hydrogen peroxide. I would take 3.8 milliliters of it, and then I would add enough water until it makes 125 milliliters, and then it would be 3%. Okay, so those are the 3 percentage volumes. The other ways, 2 ways that you'll see concentration expressed that as in society in life are parts per million and parts per billion, right? So if you've ever had for example mineral water and you look at the side of the mineral water, it will have the minerals listed in parts per million or parts per billion. The other situation that you'll see parts per million and parts per billion is when we are looking at pollution, especially like water pollution. Their contaminants are only allowed in our drinking water in very, very, very small amounts. So they would be listed, the acceptable levels, the maximum acceptable concentrations of contaminants in our drinking water would be listed in parts per million or parts per billion. And this is the way that we would express really small amounts of solute, especially if the solute is something like lead. We don't want a lot of lead in our drinking water. That's not good for us. So this says if a person has 10 parts per million of a substance in their body and their body mass is 50 kilograms, what mass of the substance are they carrying? Okay, so they to solve this, they've given us the ppm number, right? So we have our formula, parts per million is the mass of the solute over the mass of the solution times 10 to the power of 6. Why 10 to the power of 6? Because 10 to the power of 6 is 1 million, right? Or there's parts per billion. Mass of solute over mass of solution times 10 to the 9. Why? 10 to the 9 is 1 billion. Makes sense, right? Okay, so if a person has 10 parts per million, right? So what does that mean? If you examine a million particles in this person's body, 10 of them will be, the substance, the medication or whatever. Okay? So we have the mass of the solute over the mass of the solution. Okay? So this person's body is the solution, right? That medication that's at 10 parts per million is dissolved in their entire body. Okay? So the mass of the solution is 50 kilograms. And then we would rearrange. We would need to find the mass of the solute. Okay? So what we have to do when we're isolating something that's in a chemical formula is we have to look at the two things that are on the same side of it, of the chemical formula, as the thing we're trying to solve for, and we need to move them. Okay? So we need to move them to the other side. And when they go to the other side, they're going to be doing the opposite operation of what they're doing on the side with like the mass of the solute. So the 10 to the 6 is being multiplied. So when we move it to the other side, it's going to be divided. And the 50 kilograms is divided. So when we move it to the other side, it's going to be multiplied. Okay? So this is how we rearrange that formula. And when we multiply everything out, we end up having 0.50 grams of solute. No, sorry. We end up having 500,000 grams of solute. And then, oh no. No, we're correct. Sorry. Yes, we have 500,000 grams divided by 10 to the 6, divided by a million. So we have 0.5 grams. So if somebody has 10 parts per million and their mass is 50 kilograms, they only have 0.5 grams in their body, right? And that's why I say parts per million is used to describe really small amounts. So they're carrying 0.500 grams of the substance in their body. And that's it. We don't need to convert kilograms to grams or anything. Oh no, did we? Did we do that? Yes, we did. Sorry. Yes. So, my apologies. So there, in order to find this amount in grams, we need to multiply by conversion factor. So there's 1,000 grams in 1 kilogram. Right, so it's 50 times 10 times 1,000 divided by a million. And then we get 0.50 grams of substance in the body. Okay. More fun homework on the next page, and I will make a separate video for that.